I've never tried actually using the Keynote remote on the phone, so we'll see how this works. So I just said, my name is Raffi Krikorian. I'm the VP of Platform Engineering at Twitter. Platform engineering is about a third of Twitter's engineering team. So we're about 300 or so engineers, and we cover everything from the back-end scalable storage systems of Twitter. So like, there's a MySQL team, there's a Cassandra team, there's a team for a storage system we call Manhattan, which is our scalable key value store. It's basically a replacement for Cassandra. All the way up to things that we would call like the timeline service, or the user service, or the tweet service. Basically, I started at Twitter over 4 years ago as a developer on the API. I'm one of the people who created the /1 API for Twitter. And we had a theory, but one of the theories we had back then is that we should maybe base the entire site on the API. Like, we were running an API for third parties to go use, why not also use it internally? So we did that. We then continued growing the infrastructure around the API to the point that I now run basically all the core infrastructure and the platform which Twitter applications are built on top of, and all our acquisitions are now leveraging in some way, shape, or form. So this talk is basically the story of what we needed to do to rebuild Twitter from the ground up. But I think, generally just interrupt me, ask me questions. I'm happy to go in any direction you want. I have this slide deck, but I don't know what you guys really want to hear. I've been around Twitter for a while. I'm very fortunate to see one of those challenges of scaling infrastructure to web scale in some ways. So if you wanted me to go in a different tangent of what I'm talking about, just tell me, and that's fine. So given that, I think, let me start with a quick history lesson, I guess. So this is the first view of what Twitter looked like. This is Jack's original sketch of what the Twitter interface should do. We very much thought of Twitter, when I joined at least, as a website that you would go use and sort of update your information, and we'd figure out a way to get that to other people. It was a destination for people to go use twitter.com. What it's evolved into is more of a platform that people communicate with the world. So this is a classic example that we like to use. I was actually in the New York Times building a few days after this event happened. From the New York Times building, you can see where in the Hudson River the plane went down. And the New York Times would told me at the time, it took them 45 minutes. They could see the plane sitting in the river. It took them 45 minutes to get it on the NewYorkTimes.com. Whereas one guy in a ferry going toward the airplane can tweet it out to the world. This is one of our most retweeted tweets on the platform today. So this is what we think of Twitter these days as. It's a content syndication platform. It's basically an event-driven system that people are generating information. We're figuring out a way to syndicate them out to the world. To give you a view of how I think of Twitter, I sort of have this graph. So Twitter has a very interesting cycle. It's sort of like a double hump cycle. This is about 24 hours. You can think of that as midnight PST, give or take, and that's the next midnight PST. And you see these two bumps. The first bump is sometime around 8 a.m. Pacific time, and that really, we call that peak. That's when basically New York comes online. That's basically when the entire Eastern Seaboard comes online. New York is in the same time zone as Rio de Janeiro, so like they're sort of like waking up and doing their thing. And it continues on through around 8 a.m. our time on the Pacific side. So like basically what's happening is a confluence of time zones. So right now, around that time when we call peak, people on the West Coast are getting to work, so they're tweeting on the way to work. People on the East Coast are going to have lunch, so they're like away from their desks and they're tweeting. Rio's in the same time zone. Brazil's a massive tweeting environment, so they're all tweeting about lunch. People in Britain are out getting drunk. It's around 6 o'clock their time, so they're all drunk tweeting. And if you circle around the globe, everyone in Tokyo is literally saying good night. Like, you should just do a Twitter search for good night in Japanese around that time. It's a little ridiculous. So that's what we sort of see on a day-to-day cycle. If it ever changes, then it usually tells me one of two things. It usually tells me something broke and shit hit the fan and we should probably take a look at it. Or something interesting is happening on Twitter. And something interesting ends up looking something like that. So that particular graph is the Super Bowl this year. So you can see, like, those spikes are exactly, I think the middle one is halftime, the last one is the end of game. So we see events like this. So these are what we call what happens in the world happens on Twitter. The story I also like to tell is I actually found out about the Fukushima earthquake by watching the graphs from the data center. It was a weekend our time. I have no life, so I'm sitting there watching the data center graphs on the couch, and I call the knock because I'm like, why is the Japanese cluster redlining all of a sudden? And they're like, I don't know. And they sort of do a quick search, it's like, there's an earthquake in Japan. So like the way that you find out things are going on in the world is you see this massive traffic spikes coming into Twitter. So these are what happens today. Like the most recent one is what we call the Castle in the Sky event. Yeah?
Is that data available for people?
In what sense? Sorry, the question is the data available?
Like, you know, if you were like a news service who wanted to find out before everyone else found out.
Yeah.
Is there a spike? There is a spike in Japan.
So that's a great question. What we do is we actually have a syndicated product. So what we call, internally we call it Hosebird. To the rest of the world it's called the fire hose. Everything on Twitter has a bird associated with it at some point. So for companies that have access to the fire hose, they just sort of watch tweet volume. And sort of like, when a tweet hits the system, the SLA is something about 110 milliseconds that'll show up out of the Hosebird stream. There's about 1 million open sockets to the Hosebird cluster at any given time. So you can just watch the volume of events coming out of Hosebird. There are some really interesting companies that have built some cool stuff on it. Data is one great one in New York City. And what they do is they actually sell a terminal that'll sit next to your NASDAQ trading terminal. And they will try to identify newsworthy events before it hits the rest of the news cycle. So like you can actually do trades if you had Data as a product based on Twitter data. You can actually do trades in that small window before anyone else knows about it. It's actually a really cool product. I kind of like recommend you all check it out. But so anyone can have access to that kind of Twitter data. You may not have access to the fire hose. In fact, a lot of people have trouble accessing the fire hose. Like we're pushing, I want to say 35 megabit a second out of the fire hose these days. So it's hard for everyone. It's hard for anyone to hold a connection to it these days. But we offer reduced sample streams. So like we will send you like one out of every 10 tweets or something. We'll just decimate the stream down, and then you can just see those still spike, and you can figure out what's going on.
Thank you.
So the way I like to tell the story is that this is a visualization of the World Cup, the last World Cup, not the upcoming one, obviously. And you can see sort of in the background those spikes in the tweet stream. And every one of those spikes that you see is basically a shot on goal. It's a yellow card being given out. There's a red card being given out. There's a team celebrating. When this happened at Twitter, I showed up maybe a year before this. When this happened at Twitter, we were under incredible duress. Like the site would be going down every single time one of these events occurred. In fact, the engineering team would be rooting against shots on goal because you don't want to have to take the site, like figure out how to get the site back up and running again. Like this was in South Africa, so we would be showing up at the office at like 3 o'clock in the morning. And we just sort of like watch the game, sort of like watch the graphs. We had a war room which had a big projection with all the graphs about the data center going on, and just sort of like hold on to your horses. Like if Brazil and Japan were ever playing against each other, then like it's probably best not to be on call that day because that day is probably going to suck. But this is again another, like this cycle of events is what caused us to really rethink how we wanted to build Twitter. Twitter at this point was the world's largest Ruby on Rails site. And this was caused, we were under so much duress during this time that it really made us want to rethink how it gets done. And also, around this time, the president of Russia decided to show up on Twitter. And literally showed up during one of the games. And he wanted to send his first inaugural tweet to the world. We had to stand up a staging site for him to tweet against. Like, we brought up a new internal site in the data center, pointed him to it, and only him. We talked to the production databases just to guarantee that he could do it in case someone scored a goal during the World Cup. Like, we didn't want to take the chance that the president of Russia couldn't actually send his first tweet. That would be embarrassing. Especially big Secret Service agents. So these two events really caused us to really rethink how we wanted to build Twitter itself. So at the time, just to give you a sense, our Twitter architecture looked kind of like this. So I like to think of the world as a 4-tier architecture. I don't know how you guys want to think of the world. But then we had a bunch of database systems in the back. They're all code names here, but I'll let you know what they are. T-Bird is where we store our tweets. T-Flock is where we store timelines. Darkwing is where we store users. And Flock is where we store the social graph. And we had one big monolithic Ruby code base that we lovingly call the monorail. And this just wasn't working for us at the time. Like this is what we deployed a monorail instance on every single machine in the data center. And every time someone made a code change, we would redeploy the entire cluster in the data center to try to get the new code base out there. And this was failing us. It was failing us pretty badly. So we really wanted to rethink how we could do that. And our big problems really came down to a few. The monolithic application was problematic for us. It meant that every single person had to be an expert in the entire system in order to make a change in it. No matter how well you want to factor the code base, no matter how well you want to give ownership to certain classes and certain modules to people, the interactions get complex. And when you have 100 developers at the time trying to write code and trying to launch features, it gets really crazy. And when you're trying to also do it and make sure it's optimal for production scale at Twitter, it gets even more insane. And basically, we just didn't have enough experts all through the system, all through Twitter, in order to make this work for us. We had a massive throughput on storage problem also. So like when I first showed up at Twitter, we were running all of the tweets out of a single MySQL database. In fact, my first coding task at Twitter was to figure out how to shard the database. And what we did is what we call temporal sharding. So once one database filled up, our DBAs would spin up another database. We would repoint the entire cluster to the next database. We just kept on going until it filled up, and then we'd keep on moving down the line. The first time we sharded that way, we had about a month before we filled up the next database. And by the time we were starting to get nervous when it would take us less than a week to fill up a database and we had to shard again. So we had a throughput on storage problem. MySQL just wasn't cutting it for us in that configuration. We were embarrassingly just throwing machines at the problem. So Rails was having trouble scaling for us. So instead of actually fixing it, we would just buy more machines and rack them into the data centers. As you all know, engineers feel dirty when they do this. Like, there must be a better way to go about that. So we were, as the engineering team, we weren't very happy with it. And you could predict the finance team was going to get pretty unhappy with it at some point too. And finally, we felt that we locked ourselves into an optimization corner. And what I mean by that is, we had taken a Rails code base and done some ungodly things to it. Like, none of you would recognize it as a Rails code base anymore. And we've pushed it so far into one direction that we've lost all flexibility. In some ways, optimization and flexibility are counter to each other, and we've lost all the flexibility as we sort of pushed ourselves into the optimization corner. So we as an engineering team, especially given the events of the World Cup, especially given the events of the president of Russia showing up, we really wanted to take an opportunity once the World Cup was over to rethink how we wanted to build all of Twitter. We had a unique opportunity. We knew we were about to grow, so we had a crucial amount of time that we could actually try and make a sort of dent in that curve. So what did we try to achieve in this process? Like, we really wanted to have orders of magnitude wins in efficiency, performance, and reliability. We really wanted to have what we call a separation of concerns. So I wanted to be able to run multiple teams building different features at any given time. In the monolithic code base, we were almost becoming single-threaded. It was almost that we could only work on one feature at a time, and that just wasn't cutting it for what Twitter wanted to get done. And finally, we just wanted to launch features faster. Like right now, Twitter is actually launching features pretty fast, I would say. Back then, there was actually a year-long stint where we didn't launch anything new on Twitter.com. And that was probably because we were sort of tied up in our code base. So how do we want to approach this? So first we had to figure out what do we really think about as our architecture. So like we trade in a couple of different things. Like we trade in CPU, we trade in RAM, we trade in network, and we trade in what we call machine density. So like these are really the variables we had to play with. So if you look at the space, and if you look at the way we were using Rails, a single box was maxed out on CPU, maxed out on RAM, but hardly was pushing anything in network. Like we were getting something in the order of 200 to 300 requests a second out of a single Rails box. Not quite good enough for us. We really want to change that equation in some way. I'm willing to trade some RAM and some CPU to get more performance if I had to, but Rails just wasn't giving us that ability. So we really wanted to figure out a way to do that. One of our engineers had an idea that we should just try to see how fast we can push a Java server, a very simple Java server. Twitter is actually theoretically not a complicated problem. So how fast can we push a single server? So we got 200 to 300 requests per second coming out of our Java boxes. So in our first prototype of rebuilding Twitter, we were pushing 20,000 requests a second out of a single box. So like we figured out how to get our order of magnitude change. The question is like, how is we going to deploy this into production? In fact, the first rewrite of Twitter failed. Like it was almost 3 days until we were about to launch it. We passed production readiness reviews. We were ready to go with this thing. We scale tested. We built our own load testing mechanisms. 3 days before we decided to launch it, we pulled the plug on it. Like we were just uncomfortable at sort of operating something like this at scale. What we tried to do is we were actually going to build a massive cache around Twitter so that most users wouldn't ever actually hit the Rails stack anymore. They would just be served at a massive cache. And that's mostly works. You can think of every single time a tweet comes in, you sort of refresh the cache. Like we're building a faster Akamai in some way. But just the operations of that, like what happens if the cache tier goes down, like we would just thunder and herd onto our backend server. So like we decided that we actually didn't want to ship this thing. We want to try something slightly different. So just to clarify, this is where the Rails guys all hate me. By no means am I saying that Rails doesn't work. Just to be really clear. I think what I'm saying is that Rails doesn't work for Twitter. Rails doesn't work for an organization that now has 1,000 software engineers poking at the code base. Rails doesn't work when you have couples of thousands of machines in the data center that you want to manage and try and manage them efficiently and cost effectively. So what we instead wanted to go do was try to figure out like what really our problems were and try to figure out how we wanted to solve them. So our biggest problems was that we have what we call a server workload, and Rails just wasn't built for that kind of server workload. We have a huge number of concurrent connections. At any given time coming into the data center, we're doing hundreds of thousands of requests a second, sometimes on the order of millions of requests a second coming into the data center. And that just wasn't efficient for Rails, especially because the Ruby VM is single-threaded effectively. So it means it can only manage one request coming at a time, and the way you're going to get multiple requests coming into Ruby VM is that you literally spawn a bunch of different processes on our box. This is the case back when we were evaluating this. Ruby has changed slightly since then. Another one is that we just have tons of I/O coming in and out of the data center. Like I was saying, for our streaming API, we're pushing on the order of 35 megabits a second. You can just imagine how many requests are coming in and the payloads we have to ship in and out. Like we're shipping API requests in and out at the scale of about 1 million requests a second. And finally, we have very few persistent objects in our system. Like basically, it's all a request response model, and Twitter is actually a very simple conceptually system. A request is going to come in, we're going to serve a bunch of responses back, and they just want to dump the stack and start over again. So Ruby wasn't sort of set up for us in this process. In fact, we even tried a small diversion. We built our own Ruby interpreter, and we called it Kiji. And Kiji was basically a Ruby VM with a much better garbage collection mechanism than most other people had deployed. Kiji is actually open source. I think most people can use it today, but it's Ruby 1.8, so I'm not sure most people want to use it these days. That's actually one of the optimization corners we got stuck in on Twitter, is that we built our entire stack on Ruby 1.8, and now we just can't get off it quite easily. And since we also built our own Ruby interpreter, it's hard to move to a different Ruby interpreter, but that's a different problem. So we decided that we wanted to try the JVM. JVM actually gave us a bunch of different opportunities. One of them is that we can run multiple languages on this thing. So we run, right now in production, we're running Java, Scala, and Clojure on the JVM. I've had to talk people off the cliff of deploying Cloud Haskell and other things like that. I have a rule now, since I get to run the show, I have a rule now that if you're going to introduce a new language into Twitter, you have to take one language out. So that rarely happens. So right now I can stick with 3 languages inside the data center. In fact, all production traffic is only, all transactional production traffic at Twitter is actually only Ruby, Java, and Scala. Clojure is not taking production transactional traffic for us. We have some Python in the data center, but it's also not taking production transactional traffic except for TweetDeck and Vine, I suppose. So we wanted to go toward the JVM. JVM not only gives multiple languages, it gives a real concurrency model. Like we can actually run threads like inside the data center. Like threads is a very scary thing for most people, so we had to figure out a way to make it not so scary for the number of developers we had, but I'll get to that in a bit. So just to be clear, as I told you the problems we wanted to solve, and for us, we really wanted to handle what we call the server workload. We really wanted that flexibility in the language. I really wanted to give engineers the ability to pick the best tool for the job, which is how Clojure showed up inside our data center. And I really wanted them just to like play, basically like have fun in whatever you wanted to do and try to figure out the best thing that they want to deploy into a DC at a time. So prototyping, we can prototype anything we want. I have a JVM team whose whole job is to qualify JVM on different hardware that we might deploy in the data center so that my engineers don't ever have to worry about hardware again. So that just gives me so much flexibility in what I want to do. And then finally, like I said, it gives me a real concurrency model. To manage all this, that's where we introduced something called Finagle. So Marius Eriksson and Nick Callan, two of my most senior engineers at the time, really came across the the realization that we needed to standardize the way Twitter was going to talk to the network. If we just allowed people to open server sockets, open threads, and do everything like that, then it would be a total mess in our code base because everyone would be doing something slightly different. People wouldn't be fluid within Twitter. They couldn't just join whatever team they wanted to join. And we couldn't just spin on a dime if I wanted to. So Nick Callan and Marius sat down and built Finagle for us so we had a single unified way to think about networking at Twitter. No engineer at Twitter ever opens a server socket directly. No engineer at Twitter opens a socket directly. Instead, we use Finagle to do all the communication for us. In fact, we have, and I'll add a slide for it, we have a front-end tier, basically our layer 7 router in front of all of Twitter, and it's just basically one big Finagle instance. It's a couple hundred JVMs deployed to accept all production traffic coming to Twitter, and Finagle is used to route all that traffic inside the data center and data centers worldwide. To give you a sense of what Finagle does for us, we can do a few things with it, and we just don't have to worry about it anymore. And the beauty about it is that I can make one code line change in our code base, and all the services at Twitter start to behave slightly differently. So Finagle handles connections for us in the sense that I don't have to worry. When you're writing code at Twitter, you don't have to worry about how many different sockets you want to open to the server at a given time. You don't have to worry about retry logic. Finagle will handle that for us. I don't have to worry about protocols. We use Thrift internally at Twitter. If I wanted to upgrade that to protobuf, it's a one-line change, and all of Twitter could be upgraded to protobuf in one shot. We don't have to worry about error handling because Finagle does a very consistent retry mechanism for us and a very consistent way of handling connection failures and things like that. And finally, we also don't have to worry about service discovery. Since you never open a socket at Twitter, the way that we actually address things within the data center is that you say, I need a connection to the timeline service. And then Finagle will figure out which machine the timeline service is on, which machines, because it's going to be a cluster, which one of those machines is the least loaded, and then I'll pick that machine for you to connect to. We just don't have to worry about DNS or anything within our systems anymore. And finally, it also gives us something we call observability. I'll show you what that looks like. I have a few screenshots of our observability interface, but it shows you exactly how the system is performing at any given time. The one thing I have to do is sort of like warn anyone who listens to me talk about this stuff is like Twitter's built a bunch of fundamental infrastructure from the scratch and sort of like deployed into our data centers. And we did that because most other systems just never scaled for us. Like we've evaluated almost everything. Like we have our own custom version of Memcache that we run in the data center because stock Memcache doesn't cut it for us. We have our own custom version of Redis. We have our own custom version of MySQL that we run inside data center. We're really good about open sourcing it, so if any of you want to use our code, you're more than welcome to. Finagle, though, is one of the pieces of software we're the most proud of. Like, it's been adopted by Tumblr, Foursquare, and a bunch of other companies that use it as their networking interface as well. We think it's a really, really good piece of software. If any of you are thinking about doing high transactional workloads on Java, even if I didn't work at Twitter, I'd recommend you use Finagle, because we think it's that good. So, just to look at what it would take to open a server socket effectively at Twitter. So this is in Scala, but we can sort of make our way through it. Sorry. Just to walk down it. When you build a server at Twitter, you sort of give it a name. You would call it whatever you want, service name. We have one service, obviously, it's called timeline service. You tell it that you want to report all statistics to a particular stats receiver. I'll show you what that looks like visually, but it means that all errors, all exceptions, everything about it would go to that stats receiver so we can visualize it and understand what the cluster is doing. The Zipkin tracer, again, I'll show you a screenshot of it, but it's basically our data center level debugger. We're telling it specifically that we want to open an HTTP socket, so it'll automatically open by default on port 80. It also means that it'll automatically instantiate the HTTP codec, so it's actually taking HTTP 1.1 connections. We tell it we want only up to 1,000 concurrent requests with half a second delay, and then we tell it we want to build a particular request response mechanism. We don't actually issue raw HTTP requests. Finagle will sort of wrap it for us. Like, we could change that codec line to Thrift. We could change that codec line to Protobuf, and Finagle will just figure it out for us. We're not worried about ever having to write those kind of connections again. And then when we deploy something like that, we then get a whole slew of statistics on how well the data center is running. We get very consistent error handling throughout the entire data center, and we just get to manage in a very consistent way how all of Twitter is running and operating. And again, if I have a security problem, we can just sort of make a one-line deploy or redeploy Finagle, and then all the data center can pick it up, and we don't have to worry about whether or not this particular service handles retries differently than that service. So we can just reason about the system. When we went from a monolith world, instead of just having one service with 4 backends, we actually went to something that looks a little crazy. So once we removed the monorail, we then sort of deployed a whole slew of services into Twitter that's connected in a whole bunch of different ways. So this is obviously only a snapshot of it. But we basically took all the logic tier of Twitter and broke it out into 4 core services. So again, these are all their code names, and you can see the ridiculousness of them. TweetyPie is what we call the tweet service. This thing does a couple of million tweets a second come out of it. It's basically fronting a massive cache, a couple terabytes of RAM. Maybe about the last 2 weeks of tweets are in the TweetyPie cache at any given time. You can ask TweetyPie for any tweet from any date from any person, and it'll figure out how to get it for you, whether it means it has to hit the cache for it, whether it means it has to hit a database for it, whether it's going to pull it from HDFS, what other annotations it needs to get from it. TweetyPie will figure that out for you. So we expose a Thrift interface so that any developer within Twitter can write something interesting about tweets and not have to worry about where they come from. The same thing goes for Gizmoduck. Gizmoduck's our user service. Every single user in Twitter is held in RAM. So we don't ever have to hit databases in order to get user information. Gizmoduck is a protection mechanism. Maybe about once a day, it'll basically flush itself and reload from the databases, just as a protection against inconsistencies. But basically, we just don't worry about whether or not we're ever going to hit a DB to serve user data. We can just get it from Gizmoduck, and Gizmoduck will figure out everything about a user. It knows the last time a user logged in. It has a general idea of the last IP address the user came from. It knows the last tweet the user sent, or at least has a pointer to TweetyPie to figure out what the last tweet it sent, things like that. TLS is our timeline service. It's what composes your home timeline. And the social graph service is exactly what the social graph service. At some point in Twitter's history, we got frustrated with code names and we just started naming things appropriately. So the social graph service actually contains all the connections between users. There's a multitude of different graphs at Twitter. Most of you are familiar with the following or being followed by graph, but we also have a device follow graph. So like when Lady Gaga tweets, I know which phones around the world I need to ring up. We have a blocking graph. So if you block someone, I have all that recorded in a separate graph. The social graph service manages that for me. The monorail is still here, but in a much smaller form. So we're still the world's largest Ruby on Rails site, even though the monorail is actually serving less than 7% of our production traffic today. And then Woodstar has been a replacement for the monorail. So Woodstar contains all the APIs that serve Twitter at its scale. And the efficiency gain we've gotten with this model is a little ridiculous. It's about 12x of the number of machines efficiency. So we are serving, well, I'm not going to tell you the exact numbers, but I can tell you we're serving 7% of site traffic on about the same number of boxes that we serve 93% of site traffic on Woodstar cluster running in the JVM.
Yeah, you mentioned on your cache machine you had terabytes of RAM.
Yeah.
You mean like an SSD file system type?
No, literally terabytes of RAM. So like,
Who makes such a system?
oh, I mean, it's over a couple hundred machines.
Oh,
So,
okay.
so the TweetPy cache cluster is a couple hundred, in this case, memcache machines that are also replicated. So we have 2 copies of every single tweet somewhere in the data center, so we can survive rack failures or power failures. At Twitter scale, a machine a day is easily crapping out. So we want to make sure we don't have to worry about those problems. And the timeline service, for example, fronts all of your home timelines. Every active user's home timeline is in RAM at any given time. In fact, it's in RAM in 3 places in every single data center, so that we just don't have to reconstruct your home timeline. That's why actually when you go to twitter.com and log in, your home timeline shows up really quickly, is because all of it's just in RAM.
Is GizmoDuck memcache on Finagle or memcache native?
Everything is memcache on Finagle. So the memcache servers itself are basically just memcache. We have twemcache because we can proxy, do replication, things like that. And then we have Finagle memcache, which is our memcache client that can talk to the memcache servers for us. We've actually recently started deploying a whole cache as a service system within Twitter, so that you actually hit a cache proxy and it'll figure out which cache cluster it wants it in, and then we can actually do sort of costing of how much caches cost us. But basically the whole logic tier at Twitter is one massive cache tier. Like Twitter's SLAs are a little ridiculous. Like I want to be able to return a home timeline. Like I wanted you to be able to ask the timeline service for Raffi's home timeline and have it return in about 10 milliseconds. So that means like everything in Twitter is just in cache at any given time. And if we were to lose a machine, then we can fall back to back-end databases. And we, as I said before, we proactively clear our caches every once in a while. But so yeah, the monorail cluster, about 7% of site traffic. Woodstar cluster, about 93% of site traffic. There's a few other services I haven't listed there. And they take about the same number of machines to run them these days, which just shows you the efficiency between the Ruby stack and the Java stack. The TFE here at the end, that actually does our massive routing within Twitter. So every request comes into our data centers. They hit a load balancer first. The load balancer, all it effectively does for us is do DDoS protection. And then it goes, hits the TFE, and the TFE makes a global decision of where should this request go. So if you're asking for home timelines, it's probably going to go to the Woodstar cluster. The question is which Woodstar cluster, where in the world? So as you come into the TFE, it'll make a global decision of like, it should go into data center 4, and it'll be routed across a backlink somewhere else and sort of hit the cluster back there. So the TFEs can make these global decisions for us. The TFEs are also our mechanisms to do data center failover. So I can tell a TFE I need to turn the data center off, and it'll start flushing all its connections to a different data center for us. So we can then do maintenance if I have to.
Excuse me.
Yeah?
Do some sort of optimization based on like the network, the bandwidth, and whatever to figure out your data centers?
Sure.
Could you kind of talk about that just a little bit? It's industrial engineering background, so I'm kind of interested.
I mean, so we think about data centers in a few ways. So we think about them as redundancy for all of us. We also think about them as how to get data closer to the users. So we do that in a couple of different ways. One of them is you can deploy a data center. Data centers have data that we can just serve. The other way, so we do a cost-benefit analysis of like where are users coming from, where can we put them, what do backlinks look like, how much does bandwidth cost much as power costs, and then we can figure out what we want, where we want to place data centers. When you place them internationally, then there's regulatory issues you also have to worry about. That sucks. But we also, as a way of managing latency, is we deploy what we call POPs, points of presence, around the world. And what we do there is we simply deploy load balancers across the world, so we can do in-country SSL termination. SSL requires a bunch of hops in order to complete the connection, so we just do those connections. Like, for example, I'm not saying we have one, but a good example would be a load balancer in India. A lot of people coming from dial-up connections, doing SSL negotiation across the Pacific over a dial-up would suck really hard. So then you just allow them to do SSL negotiation in country, and then from our load balancer, we can run our long-lived connections back to our data centers. So we play multiple tricks in order to get low latency across the world. Data centers are only one of them.
Are you fronting each of your data centers with a TFE at the top of the stack?
So,
or is the load balancers really where the action is in terms of...
Load balancers, effectively, all they do for us is like layer 3 DDoS protection. They pass every single request down to the TFE, and the TFE then makes a decision what to do with it. If I could get rid of load balancers today, I would. Give me 2 years, and we'll figure out a way to do it. I mean, there's been talk about making TFEs be our load balancing cluster. We're just not there yet.
Yeah, it sounds like your TFE really is your CDN layer. So
our TFE is our, what we like to call our layer 7 router. So our TFE has some caching in it, so it can protect backend services. Our TFE also does authentication and rate limiting. So if what looks like a spammy request comes in, our TFE will just nail it before it even comes into the data center. We used to have this problem with the monorail all the time, where every single request, whether it's spammy or not, had to be processed by the monorail. And so our capacity could just be eaten up by a spammer. TFE could just nail that for us at any given time. We also have IP blacklisting support and things like that. The TFE also has knowledge of like whether a request is coming from Amazon or EC2, or whether it's coming from any of the other cloud services, so that we can then back propagate information to those cloud services.
So do you have, if you have TFEs fronting each data center, do you have those TFEs basically network to each other so they're communicating these?
So the question is, like, do the TFEs talk to each other across data centers? And the answer is yes. They have to.
Yes.
So TFEs are knowledgeable about what global topology looks like, so they can route information back and forth. Because I may choose, for example, to shut off a Woodstar cluster in a particular data center. So a request could come in because of DNS balancing, and then TFE would be like, I don't have a Woodstar, and it would ship it somewhere else in order to try to service that traffic. But as you can imagine, this kind of looks like spaghetti code, and debugging this can be a bitch and a half. So what we tried to do is figure out a way on how to actually make this, I'm sorry about this, how to make this actually understandable to all of us. So that Zipkin tracer I was telling you about gives us graphs that look like this. So I can pull open a Zipkin page within the data center, and I can give it a particular request. Every single request that comes into Twitter is tagged with a unique identifier. So given a particular request, I can get the entire trace of that request through the data center and the number of milliseconds we've spent in any one of those places.
Why you haven't retired the monorail yet if the route started working fine?
Why haven't we retired the monorail? We're in the long tail of what's left in the monorail. So like getting all that off into the Woodstar cluster, we're basically just not done. There are some features that the monorail has that Woodstar still doesn't. Granted, it's only 7% of site traffic, but that means 7% of our users. If you take Twitter's active user base and multiply it by 7%, that's still a large number of people. So we're not yet done moving all that code. We've been working every 2 years. One of the biggest problems is that Twitter is not a static target. So if I could get a commitment from the rest of Twitter not to ship any more features, I could probably have this done in half a year or so. But that's never going to happen, so therefore it's always a moving target that we're trying to catch up to. So no new features ever go into the monorail, we just haven't finished moving the old ones out yet.
For this dashboard, do you consider Elasticsearch with Kibana?
To power this dashboard?
Yeah, to power the metrics and do visualization.
I don't know is the short answer for that. So this is actually modeled after something that Google calls Dapper. So Google has a distributed tracing system that they publish papers on. So this is actually just an implementation of it that we've in turn open sourced instead. This dashboard view is actually about 2.5 years old. Our current version of this is a little more advanced than this view. This one was modeled specifically to look like debug view in Chrome, effectively to understand how that works. So, but just so we can even go through it, like this is a request going into, it looks like the timeline service. It returns in 11.2 milliseconds, and you just see the breakdown across all the different services. So like we spend about 0.3 seconds in every single one of the memcache calls, except for an incur against memcache, we spend about 1.3 milliseconds in, things like that. So this actually gives us the ability to understand how our software is performing at any given time and actually trace it through. I can also dig in a little deeper and sort of see, like, given every single request that goes to a timeline service, what's the average latency look like? And then I can actually build graphs of what does the dependency graph of Twitter look like at any given instant. With so many teams at Twitter, the topology of the Twitter infrastructure is changing on an hourly basis. This gives our network operations center some understanding, at least, of what's the latest state of the system. And we don't have to worry about tech writers sort of like catching up to the current state of the system. The knock can be like, something's going wrong with the timeline service. What's connected to the timeline service these days? And actually just trace it through the system and understand who we should be paging at any given time. I mentioned statistics at some point, so understanding speed in the data center. This is what our main dashboard looks like at any given time. So you can see this is also a few years old. I can't show the latest versions of the dashboard, but you can sort of see what TPS, tweets per second, looks like at any given moment. We can understand what latency looks like. We understand how many exceptions are being thrown. All of this is because most services at Twitter are built on Finagle and are reporting their statistics to a stats receiver that we can then just graph. I literally have one of these graphs sitting outside my office. So at any given time, I can just look up and understand what the error rate of Twitter. When I joined Twitter, the success rate sucked pretty hard. Like, I think it was like a constant thing, like we'd always be in TechCrunch because a fail-well showed up. And these days, like we have over 3 nines of reliability on the data centers. And we just, because we can see it and react to it really quickly. If any one of these graphs are deviating of what we call mean, then alerts just start automatically going off within the DC. Whenever you deploy Finagle service, you can automatically set up what the alerts should look like. In fact, the code to do it, the code to get statistics looks really simple. All you do is sort of wrap a piece of, a block of your code inside your service with something that looks like that. So we're going to tag this block of code with request latency in milliseconds. And then we can do a query against it in our observability stack. We've created our own Scala language, but you can sort of understand what goes on here. Like you can look in a timeline service, we're going to look for what status timeline looked like, and we want the P50 distribution of what the latency looked like in that request. Turns out on Twitter, we actually care about the P999. So what do 99.9% requests look like? That's what we set our SLAs against. But it's easier to reason about what the average time looks like. And then we can just sort of create these graphs on the fly. So our Viz cluster just allows us to plug in one of these statistics, and we can see the P50 latency looks like about 4 milliseconds. I can ask for the P95 latency, that looks like 7 milliseconds. I can ask for the P99 latency, and that's where it starts getting interesting. I can really start to understand like what's actually causing the deviations at the P99. So P99 for us actually means a lot. That means like 1 request out of every 100. When you're getting 1 million requests a second, that's a crap ton of requests that we're going to track down.
I don't know if you can speak about the current system, but in this system here, how frequently is that information updated, like visually?
In the current system, it auto refreshes. There's about couple second latency between when it happens in a data center, which shows up in this dashboard. The requests are collected sub-secondly. So if you have to deal with like tens of milliseconds before data actually hits the observability cluster. I know the network operations team, one of the ways we've architected our observability stack, so you have a single source of truth. It's a massive cluster, massive Manhattan cluster, which is our key value system, that collects all the statistics on the data center. So every single service is reporting into this one cluster. visualization, this viz service is only one thing we can point to it. Our alerting mechanism is another thing we can point to it. Our network operations team has built their own system, which gives them that sub-second update rate. This system gives us about 1 second update rate. 1 second turns out to still be a very long time when the site is crashing hard, because like it's like the longest second of your life to try to figure out if that fix you deployed actually made a difference.
How do you test the performance of new features?
Yeah, that's also a great question. How do you test performance of new features? So we do it 2 ways. One, we have a whole bunch of staging clusters. So we can actually deploy new services into staging clusters and either point them against mocked out backends. Mocked out backends is always a little iffy. We can't deploy another system at the scale of Twitter. That would be prohibitively expensive. So every once in a while, we actually just test in production. The current workflow basically looks like you write some code, you deploy it to a test cluster, you make sure it's correct. We have a system we call, I think now it's called Iago, it's open source, which is our load generation framework. So Iago can either play back logs or you can give it synthetic data that it'll just create on the fly. And you just sort of slam the system to basically try to figure out what's the point it breaks. Basically, we like to think of it as a dyno you might put your car on. So we like get the cluster up and running, we slam it with Iago, we turn Iago up until we find that breaking point occurred, and that's how we think of capacity on the system. And then that's how we end up deploying for performance reasons across the board. We have some minimum performance thresholds any service needs to sort of maintain. If you tell me your service can only do 10 requests a second, I'm not letting you deploy it in the data center. So like, you have to be able to do a couple hundred requests a second at the minimum in order to get into the data center. And then people figure that out using Iago. Iago, like, that works really well for when you're making a change and deploying a system that should transparently take the similar traffic. If you're deploying a new feature, then you're going to kind of guess what the workload looks like. So we try to get it right. We then deploy maybe 50% more capacity, and then we'll trim it back down later. I think one of the things I don't cover in this deck, but I'll just talk about it, is we rely on something we call Mesos inside Twitter. So we actually don't ever deploy onto raw hardware at Twitter anymore. Everything's deployed into our Mesos compute cloud. Mesos also open source as part of the Apache Foundation these days. And what Mesos allows us to do is you describe a task to the Mesos scheduler. You say, I want this task. It's going to take 10 cores. It's going to take 20 gigabytes of RAM. It can be parallelized up to 5 ways. And Mesos figures out where in the data center that code should go. And it does what we call bin packing. So if it finds another piece of software that has a very compatible profile, it'll stick them both on the same machine so we can get more efficiency out of our machines. It also means that if a machine dies in a data center, which I told you happens all the time, the Mesos scheduler will realize that and spin up another instance almost instantaneously somewhere else inside the data center. So we don't have to worry about machine failure anymore because the Mesos scheduler, Aurora, is sort of rescheduling our tasks for us at any given time. And we can then drive up efficiency in our data center because we can describe to Mesos how much we think it needs. Mesos can then also figure out how much it thinks something needs and then start bin packing closer and closer together. This is basically our cost-saving trick inside a data center.
Do you run things like Hadoop or Spark on Mesos as well?
We don't currently run Hadoop on Mesos, although that's our next biggest target. The 2 largest clusters in the data center are the Mesos cluster and Hadoop cluster. So there's seems to be some synergy you should probably figure out there. Especially, I showed you the diurnal curve of Twitter. It would be perfect to run Hadoop right in the middle of that.
So are virtual machines used, or is this just a deployment scheme?
Yeah, we don't use virtual machines at Twitter. We do raw deployment. We use Linux containers to try to manage process boundaries and try to make sure we have resource allocation, but we have no overhead from VMs. We just run everything pretty raw in the data center. Like EC2 has to run VMs because there's security implications of like you might know what else is running your data center. This is my cloud, so I don't really have those concerns.
So what is a task?
A task is a Java process, effectively. In fact, it's actually almost any process. We also have support for Ruby and Python in the Mesos cluster. There's nothing specific saying it has to be Java. We've just optimized the path so that Java is easiest to deploy. Yeah?
And if you have you can't have all the backend that you need for your load testing, how do you get the test suites out of production? Keep them
up. So when you're doing your load testing, how do you make sure those don't get mixed up?
Oh, fair question.
Tweets as well.
Yeah, sure. I didn't finish answering that question. That's fair. So you don't is the one answer to it. So sometimes if you have to do a load test on a production service that could write traffic, we just need to be very careful so we know which traffic we're going to mark as testing traffic. Thankfully, things like our zip and tracer allows us to tag traffic even all the way down to the databases, so we can filter them out if we had to back there. We also have a whole canarying mechanism at Twitter. So once we've done these production load tests, we can actually deploy new code onto 1 or 2 boxes in the data center, just let it run for a couple of days, and just get a better feel of how it might operate in that situation.
How has this, I know you kind of alluded to it earlier, but how has this new structure improved, or to what quantity has it improved your release cadence?
Yeah, I'll touch upon that at the end, but I think like the short answer is a lot. So just to simplify for a second. So this is the TFE to Woodstar cluster, for example. So a web page comes in, hits the TFE, which will then hit Woodstar. What we had to do is to figure out how we wanted to actually shift traffic from the monorail to Woodstar. Our job was to do it as transparently as possible. We can never take downtime on Twitter to our end users. People rely on Twitter for not only celebration, but also world disaster events. So elections are celebrated on Twitter, earthquakes are mourned on Twitter. So we can never take downtime. So we had to figure out a way to sort of change the wings on our flying airplane. And what we did is sort of using the TFE and then using a system that we call Decider, we wanted to move traffic between the 2 different clusters. So we got ourselves into this configuration for a while. And what the TFE would do is it would allow us to what we call dark read against Woodstar. So we actually request to come into TFE and we would tee it out to the 2 different clusters, and TFE would compare for us the results. We ran like this for a couple months actually. So a request would come in for a home timeline. We doubly issue those requests. We'd issue one to the monorail cluster and one to the Woodstar cluster. We look at what performance looked like and we look at what correctness looked like. And when we surpassed 3 nines of correctness, we'd be constantly deploying to try to get there. Then we started actually trying to shift traffic between the 2 until we got to 100% Woodstar. And we did that over the course of 2 weeks. So we just sort of moved what we call light traffic over to 2 different clusters. And this is actually how we now deploy almost every service within Twitter, is we never actually deploy everything to 100%. A service goes into production behind what we call a decider. And decider is controlled by a dashboard that looks like this. And you can see all the features for Woodstar anyway on the left-hand side. And then you can just plug in what percentage of traffic you want to be sending to that. And the TFE will start routing that traffic very slowly across the services. Or you can do it internal to a service. So for example, we launched the conversations on Twitter, that blue line you see on the side. And we launched that over the course of 2 days. So we launched it to 1% users first, saw how the service reacted. We went up to 5%. And then you get a bit bold. After that, you go 10, 15, 20, and you just ramp it all the way up. And you do that over the course of 2 days to make sure the backend service warms up, the caches warm up, and everything sort of just progresses normally. We give this dashboard also to the network operations team because they can see what's going wrong in the zipkin traces and just shut things off without ever having to do a code deploy. We want to minimize the number of deploys we do in a cluster, but we want to give as much runtime configuration as we possibly can. So, to answer your question, it's like, where are we today with all these changes? So like this work has been 2 years in the making. And sort of now we're what we call a team organization that mimics our stack. So right when we were running on the monorail, we basically had one team, one engineering team that worked on the monorail, and we had 4 database teams that worked on storage systems. Now every one of those boxes I showed you actually has an engineering team behind it that deeply understands that portion of the code base, deeply understands that portion of the system. And they work out APIs between all different teams at Twitter. So if you need a new feature on a tweet, you just talk to a TweetPy team and they'll get you in their next sprint and they'll put that feature in the tweet for you. You don't have to be an expert at Twitter of how all tweets work. You just need to be an expert on your particular feature, and we can just run these teams as independently as we possibly can. There are certain teams that get collided on, the tweet team being one of them, the timeline team being one of them, but then those teams are just generally the larger teams at Twitter. So we can actually have more feature throughput on those. And then now we're able to launch massive features in parallel. Every time we launch a new mobile client release, there's actually 10 or 12 different features in it that we're able to build over whatever course of time because we have 10 or 12 different teams now working on it, something we were never able to do before. And statistics-wise, we're just a lot faster. So like these are the blue line is the dark blue, is the monorail, and the light blue is the Woodstar cluster right now. So our performance in milliseconds has drastically improved for the average case, and it's also pretty good in the outlier case. And this also doesn't capture machine efficiency, which is something like a 12x machine gain for us by simply moving to the Java stack. And just to sort of close on some statistics, like I said, we're about 7 to 10% of Twitter is still on the monorail. The rest is now on the Java stack. We're a lot more performant. We're a lot more reliable. Like I was saying before, we're hitting over 3 nines fairly regularly. And now we just deploy a lot. Like we can deploy to fix bugs, and we had 50 deploys just yesterday on the system. We run hundreds of experiments now daily. Every single one of you are probably in a slightly different Twitter experience than every other one of you. And it's because we're running all of these different experiments now on Twitter, so we can really A/B test everything that we want to deploy out. This new architecture has allowed us to simply just run as fast as we possibly can. There are obviously some cons to it, but net, we think we've figured out the way we want to go forward. So that's all I have to basically say. And like, I'm happy to sit here and talk for as long as you guys will have me, I suppose. I think your hand went up first.
Yeah, question about when you guys picked Scala, and
yeah.
could you just talk about that a little bit, because that was pretty early.
Yeah, so actually Scala was picked before I showed up at Twitter. So I showed up about 4 years ago, 4 years and a couple of months. And Scala was chosen because they wanted to experiment in Java, but no one actually wanted to write Java code. We have a whole bunch of Ruby programmers, but no one. So like Ruby is this untyped language and stuff like that, and no one wanted to write statically typed language code anymore. So the entire team picked Scala because it sort of gives you what looked like an untyped language. I mean, it has a type inference engine on the back end for compilation. And it gave you a functional looking language, so it just was more fun to program in. Twitter bought a company called Surmise back in the day, which now powers Twitter search. The Surmise team still works at Twitter, most of them at least. That entire stack is actually written in Java. But all new services, all new big features are probably written in Scala these days.
How does those acquisitions, how does this kind of fit into getting them on Finagle and other things? You guys have a bunch of different people you've acquired. Do you try and reach out to them and get their stack to conform to what you're working with?
Yeah, so as you move into the data center, then you sort of you have to build to our standards to make sure it sort of scales, has the redundancy that we want. So we're in the process of moving, like we're always acquiring companies at Twitter, and whenever we do, we have a plan to sort of move them into the data centers. Usually that means, it turns out that most acquisitions are storage heavy. That's what it really comes down to. And I embarrassingly find more companies using MongoDB than I really want to see. So we spend a lot of time moving them onto our scalable storage mechanisms first, and then we worry about their compute side, which is usually a smaller problem, or at least for the companies that we acquire. So when we move their compute side, then we have a conversation about Finagle and things like that. Crash Lakes is a great example. So Crash Lakes, are moving them onto our backend storage mechanism, and then we'll work with them on moving their app tiers at some point. Yeah, you back there. Yeah.
Can you tell me limitations on API calls?
In what sense?
In a sense, like I started my first app about 3-4 years ago, and since when you guys squeezing developers, limiting a number of calls. In the latest version 1.1, I believe it's one call per 60 seconds or something.
It's one call per 60 seconds on the search API. So one of the benefits of moving to a 1.1 API is that we actually have differential rate limits. In the version 1 API, we have the same rate limit across the entire API. So now we actually can have different rate limits for different features of Twitter. And it's partially based on how expensive it is for us to serve those calls and the amount of traffic we see at any given time. Those rate limits are also dynamic, so we can change them at any given time. If you reach out and talk to us, so we can decide whether or not we want to elevate rate limits on per user or per feature basis, depending on sort of the value to the Twitter ecosystem as a whole. So rate limits are usually set by the business development team and sort of like how we want Twitter features to be propagated out into the ecosystem. Yeah.
Does Twitter do any kernel hacking for performance optimization?
Oh yeah, most certainly. I have a whole OS team whose whole job, so they do, the OS team is split into two, kernel space and user space. The kernel space team does a bunch of performance optimization, but also their main job is to work on, someone else is asking this, main job is to work on the Linux container mechanisms for us. So it's mostly resource allocation and resource limitations that my kernel team works on. And also hardware qualification. So we might buy a new platform to deploy in the data center, make sure the kernel functions properly there. But we've been bitten by performance problems in the Linux kernel many times, like most notably on the Hadoop cluster. So our kernel team will have to go debug that and figure out how to get performance up again.
Hopefully you're contributing that back.
Yeah, we are, as you go to our GitHub page, like we are extremely big proponents of open source. I have 2 members on my staff whose whole job is just to open source our software stack. So yeah, we give everything back as much as we can. All our patches do, Memcache, MySQL, Redis, and things like that. We're fairly good about giving everything back.
Hopefully the kernel too.
And the kernel too.
Another performance question. When you look at what Facebook or Google does for extreme performance, they often go to C and C++.
Sure.
What made you go solely with Java, not any parts of it in C and C++?
I mean, we're definitely experimenting with C and C++. We view it as a cost-benefit analysis, really. So, like, I don't want developers to have to worry about garbage collection, for example. I don't want them to have to worry about how to manage memory internally. So going to a language that manages that for us in a way that's already built into the language or built into the virtual machine was a huge boon for us. We could, on the other hand, invest time in building a garbage collection mechanism for C++ so that our developers don't have to worry about it also. But we just didn't think that was the right call to make at the time. We also had a lot of people who understood how the Java virtual machine works. Our CTO used to run the Java team at Oracle. So like we just know how this piece of machinery works. We had some of the original JVM team now work at Sun, now works for me on my Java team. So we just know how this machine works really, really well. We also don't want to have to worry about interactions of native code and the platform that we might be running on. Like we refresh our platforms many times a year. So when we requalify a new platform, I don't want to have to worry about does every single service work on this platform. I just want to worry does the JVM, is the JVM performant on this platform, and then our code will just follow.
Can you talk about how you use Storm within Twitter?
Sure. So Storm came from Backtap acquisition. Nathan Mars wrote it. And what we use it for is mostly offline, but still, how do I phrase this? Real-time computation that's not transactional to the website. What I mean by that. So all events that come into Twitter Data Center, like whether it be a request for a home timeline, whether it be a new tweet or stuff like that, it gets pumped through a Storm topology so that anyone within Twitter can tap into a feed of what's happening within Twitter, and then we can build a new Storm topology to do computation around it. So for example, the Discover page that you see on Twitter is actually one big Storm topology. So events come in of whether it's a tweet, retweets, favorites, stuff like that. And then the Storm topology will just increment a bunch of counters, do some computation, and then publish up what it believes to be a personalized page for every single person that might be showing up on Twitter. So our revenue team uses Storm to do all the computation on like real-time bidding on the promoted product suite. We basically use it anywhere that we have to do stream computation on Twitter. All of Twitter is basically an event-driven framework. So the transactional portion of it is what I've been describing, but anything that has to do with the back-end stream of data goes through a storm topology in some way.
What the traffic that you get, is it from iOS or Android or websites, and does it use the same mechanism underneath?
Yeah, so no matter what you come from, whether it be iOS, Android, Windows Mobile, et cetera, or the website, they hit the same API coming to Twitter. Sorry, the website's actually slightly different. Any mobile device that comes into Twitter is the same API in Twitter itself. So we can differentiate what it is. The TFE will tag them for us where it came from, but we treat everyone the same internally, so we don't have to develop one API mechanism. I can't tell you what the distribution of traffic, I'm not allowed to tell you what the distribution looks like right now on the Twitter system, but as you can probably guess, like mobile traffic is emerging faster than web traffic is, but everyone's seeing that trend these days. Yeah, you.
So if each user may or may not be subjected to kind of the A/B experiments,
sure.
At what part of the process do you handle like that kind of stickiness to the service?
Oh, yeah, the TFE will bucket you. So if you come in as a particular user, the TFE will assign you their particular bucket, and we bucket on a per user basis. So that you came in, you're in these following experiments, and you'll stay in those following experiments until we decide to either turn you off or we remove that experiment from production.
What's TFE stand for?
Well, it actually stands for the TFE front end.
You had to get recursive.
I think there's a question over there. Yeah.
Is there a plan one day to allow you to say, okay, I want to search for this hashtag on this and this date or this date range, or a particular user's nick, and say, what tweets does this person have from month 3 to 4?
So we actually call that archive search. And archive search, like you can actually search back for every single popular tweet back to the beginning of time right now. We haven't deployed it to every single tweet, only because actually it turns out not very many people want to see those tweets. So it's just an efficiency question for us. But right now, if you go to search, it's not search.twitter.com anymore, but if you go to the search bar up top and did a search for, Barack Obama, you'll find his tweets from like the 2008 election, and even before then, like still on the site right now. There was a time when we only allowed you to search the last 15 days, but we've deployed archive search as one of the new services in Twitter a couple months ago.
I missed that.
Are all home timelines fully actualized in RAM, or maybe you could talk about quality of service, and I think you see where I'm going with that one.
Yeah, sure. Every home timeline for every active user of Twitter is in RAM right now. It's in RAM in 3 different places in every single data center that user might be in. So when a tweet shows up in Twitter, the social graph is queried to figure out every single user that might follow the tweeter, and then we insert that tweet into all those people's home timelines. We might do other stuff. We might ring cell phones and things like that, but that gets inserted into the Redis cluster 3 times. And that's very carefully said active user. If you're a non-active user, you are not in RAM in the cluster right now. The home timeline is not actually persisted to disk. What we call your user timeline is persisted to disk. So every single tweet you've ever tweeted, the index of those tweets is persisted to disk. And if I needed to recreate your home timeline, I need to figure out every user you follow. I need to hit disk for all their user timelines, merge them back together, stick that into RAM. It's a very expensive process. It'll take us in the order of a couple of seconds to pull that off. So we try not to do that, but every single active user is in RAM right now. And we've experimented and played games like, should we put non-active users in RAM, or this turns out to be the best mix for us right now. So we can return a home timeline for an active user in less than 10 milliseconds. If you are a non-active user, it might take us a couple of seconds to get that timeline to cache for you.
How do you define active user?
That changes, and I'm not sure I can say right now. Yeah, you.
You mentioned you're planning to replace Cassandra. Can you talk about the shortcomings of it?
Oh yeah, Cassandra's actually great. I have almost no problems with Cassandra. Cassandra's really great for high write throughputs. The real problem is that when you get to retardedly high write throughputs, Cassandra can't rebalance itself. So that we find that the only way that our largest Cassandra clusters could ever be expanded while still taking production write traffic is to literally double a cluster. So when you have a 300 node Cassandra cluster, I have to go ask finance for 300 more machines in order for it to expand. And that it's just not a worthwhile conversation for me to have after 4 or 5 of these conversations. So we've replaced it with a system, but aside from that, we love Cassandra. Like if it weren't for that problem, we'd be fine. So we've replaced it with a system we call Manhattan. We're going to be publishing a paper on it pretty soon. And Manhattan is our more scalable key value storage mechanism that doesn't have this particular scalability problem. Manhattan also has a bunch of other really nice features for us. Like Manhattan is at its core eventually consistent, but it's a plug-in based architecture, so you can have a consistency module on it, you can have a replication module on it, and things like that. So we can actually build whatever storage mechanisms we need on top of Manhattan. In fact, we're in the process of getting rid of almost all storage at Twitter and moving it to the Manhattan cluster.
Do you have plans to open source Manhattan?
We're going to write a paper on it first. I think like our theory in open sourcing has been like if we're making big fundamental changes to libraries that we find that libraries that people will find useful, then we'll open source them. Manhattan we're reserving judgment on for a bit, only because we've only recently deployed into production, and so I'm concerned that if we were to open source it tomorrow, that then everyone would be wondering, how do I get into production? I'm like, I don't know, we only just recently did it. So like, let's get a little more operational experience with it first.
How do you guys handle versioning of services, maintaining compatibility and then technical debt?
Yeah, that's a great question. So all APIs that internally within Twitter are by definition backwards compatible with each other. So every time you deploy a new service or replacement for an old service, you have to maintain backwards compatibility with the old API. Gets kind of a pain in the butt. Like that's definitely one of the detriments to like this large service-oriented architecture is evolving really quickly. So every once in a while we just have to call a flag day where like anyone is using this service, we are just changing the API in a few days, and then we'll go put it under a decider mechanism. So like we'll decide over the new API, and then once everyone's over, we can delete some code. But yeah, like so everything by definition has to be backwards compatible for a while.
So it's per team. Per team chooses when they want to clean up their code base.
Pretty much. Like I try to give as much team in. Like the philosophy I have is like the team is the atomic unit. So like the team should just decide when they want to go do that kind of stuff. Not to coordinate with their customers. Like all their internal customers have to be on board. So that could be a minor pain in the butt also. But it is on a per team basis.
So actually, a good question about this exact topic. You have these more focused teams. How do you work as a unit? How do you work as an organization to ensure that you're meeting the common goals?
Oh, that's a great question. So like, and it's very pertinent at the beginning of the quarter. So like, beginning of the quarter, I set out for platform engineering at least, and we do it for engineering as well. Platform engineering is 1/3 of engineering. Like, what our priorities are as a company. We literally just list them out in stack ranked order, and like these include features we want to launch this quarter or stuff like that. And then every single team creates their backlog for the quarter based off of those priorities. And we go through a small roadshow. Like we literally have a poster session where every single team, like it's a science fair. Every single team is lined up somewhere around the main commons with their poster. And they all wander around and they talk for a while. It's like, oh, you're doing that, I'm doing that. And they just make corrections on the fly. And that's the plan that we sort of execute against for the next quarter or so. We have project and program managers that also wander around to make sure that our high-value projects, basically my top 10 list, actually get coordinated and done, so they manage the schedule for those. And we have product managers that also inform what those priorities might be at any given time. But yeah, it's kind of a organized chaos situation. Trying to get the best of both worlds, so we do the best we can.
Last question.
Last question.
So I'm doing a Spike right now. I'm evaluating Storm versus Spark. And
Sure.
I was wondering, have you noticed in Storm that mutable state could be updated more than once, and also that you could lose the mutable state?
Have you looked at the Trident API yet?
I haven't looked at it.
Yeah, so like we have an API on top of Storm that we call Trident. So Storm itself, that's definitely the case. Trident is an abstraction on top of Storm for us that prevents that from happening. Like the way that software is usually built at Twitter is like the first layer is eventually consistent minus some errors, and then, but that there are performance reasons you might want to tolerate those type of errors. And then we got a layer on top of it, stricter guarantees, and those guarantees might come at a trade-off of performance. So Trident is a layer on top that you can use to help prevent that from happening. Cool. Thank you.